We are considering half-life. What is half-life? Let's say this is, for example, a radioactive nuclei. This is an unstable nuclei and it has to decay. Fine. So let's say there are 100 such atoms. I'm having 100 such atoms, and time these atoms take to decompose to 50 would be half-life. I can write T half. So half-life is the time required by any radioactive sample to reduce to half of the original value. See, you can see in this animation, these red dots, these red circular atoms were initial atoms. They were the parent nuclei that has to show some radioactivity, and these changed colors, blue color or violet color, what you can say is, these atoms are primarily those atoms which have been decayed. So as you can see from the clock here, what is happening after every 4 seconds is there are a number of atoms changing. So 4 they remain 50, then after 4 seconds they would again reduce to 25. So these two are two half lives. Now third half life would be again additional 4 seconds. So this remain 12. Now this is also important. When you can say initially they were at the second half life. Let's start from the beginning. 100. After 4 seconds, they reduce to 50. Then after 4 more seconds, they reduce to 25. This is all half-life happening. But now after 25, what will happen? You can say, sir, half of 25 is 12.5. We do agree to this, but zero point 0.5 nuclei is not possible. See, this is not possible as what we can understand is a nucleus is a complete entity. You can have a complete nucleus or you don't have a nucleus. There is no possibility that a nuclei or a nucleus would be decayed to a half of the original nucleus. This is not possible. It is either a full nucleus or not a nucleus. So after 25, we can have 12. Similarly, if a decay atom has, for example, 9 radioactive nuclei, remember, so after 9, they would be reduced to 4, not 4.5, since zero point 0.5 is not a nucleus. So we are not approximating it, we are just thinking it logically that a radioactive sample can have a fixed or whole number of radioactive nuclei. They won't be half. Fine. Let's move forward to the decay curve. What is a decay curve? Let's say we are starting up with a graph. See, a graph that is plotted between number of radioactive nuclei and time is basically a decay curve. Initially, what is happening is we are having a line that starts from somewhere on y-axis, that is number of nuclei axis, and it leads curve downwards to the x-axis. Both the figures or both the graphs represent the same thing. Initially, it is something high, maximum value, and then it decreases. Now, what is the logic behind this decay curve? See, if you are having a radioactive sample, let's say it has originally radioactive nuclei, n number of radioactive nuclei. So what happens after certain time? This n would decrease to n by 2, and precisely that time is now known as half-life. This is what we have learned in the previous slide. So if we plot a graph between number of nuclei and time, see it would be a decreasing curve. As time increases, original number of atoms decreases. And we know this, if two quantities are inversely proportional, what happens? The graph between them is a curved line. So in maths, what we can see here is this curve is basically an exponential curve. And later on in your senior classes, you're going to learn what is an exponential curve, but not right now. So what we can learn right now is exponential curve. Now, what we can learn here is, for example, initially there were n number of atoms. So this graph starts from here. What happens here? This is, it becomes n by 2. So time it takes to reduce to half of the original value is first half life. Then let's say there were 100, now they are 50. Then what happens next? 50 becomes 25. This is basically twice of the half life. For example, this was the time. This was the time. This, let's say, is 0 initially at the start of the experiment. This was the time, for example, for the previous experiment, it was 4 seconds. Let's work on with the same thing. So this would be twice of 4, 8. Then this would be thrice of 4, that is 12, then it would be 4 times of 4. It may be in seconds, it may be in minutes, it may be in hours, but the decay curve is basically a relationship between time and number of nuclei. See, then what's shown here is basically certain points. See, we need to understand that radioactive decay is a random process. What do you understand by a process that is being random? This needs to be clearly understood. If you say you're talking about a random process, that means you don't know when a particular atom will have a decaying process. See, if in a sample there are thousands and thousands of atoms, you can only say this sample is radioactive, and you can say the half-life of this particular sample is so and so. Let's say, as we have discussed, so in the previous slide this was 4 seconds, but you can never say that either this atom has to decay or this atom has to decay or this atom has to decay. So the process would be randomized, and all the atoms present in a particular sample won't be decaying exactly after 4 seconds. Some might decay after 2 seconds, some might decay after 3 seconds. So this 4 seconds basically refer to the difference between initial and final values. Initially, let's say they were 100. Finally, now they are, for example, 50. So I can say my radioactive sample would have an initial count half after the half-life has been passed. But I don't know exactly what number of what type of atoms present in my sample would decay and which particular atom will decay. So if we plot a graph using a device that may be a Geiger-Müller counter and certain other devices, so we can have a particular fluctuated reading. Let's say for a particular set of explanation, what we can start up is with, let's say, a GM counter shows us readings initially 50, then it shows 26, then it might show, let's say, 14, then it might show, let's say, and so on. You can complete it up till 0. So why is it fluctuating here? See, I can say initially they were 100, fine, it may happen that they reduce 50. Now I'm not clear exactly that why they are not, why this one particular atom, it has to be 25, but why this one particular atom is not taking. So this is the process that is random in nature. So in a decay curve, you can see different points, and you can see a graph that is being plotted as a best fit curve. So the process being random leads us to this conclusion that this graph would be a best fit curve, not exactly a curve that would be having all the points on the line, as we don't know how much atoms or what atoms exactly, and particularly perfectly every half-life has to have the same number of atoms. Fine, let's move forward. There are basically multiple types of nuclear reactions. We are studying two different types. A reaction that involves a nucleus is referred to as a nuclear reaction. See, when I'm saying my reaction has to involve only a nucleus, what I mean is I'm not considering what is happening outside this nucleus. We all know that there are electrons and there are shells and there are orbits. We are not considering them right now. We are only considering a nucleus. So basically, a nuclear reaction can be either a nuclear fission reaction, as seen in this animation. We are having a nucleus, and this nucleus is is hit by a certain subatomic particle. In our case, it is neutron, and it decomposes into smaller nuclei. Let me draw it here separately. Let's say this was my nucleus, and this neutron strikes this nucleus. And what happens as a result? This nucleus breaks. This thing needs to be clearly understood. Here is in radioactivity, what we were especially discussing was beta radioactivity was all about a natural process. We were not involved in any decay. It was happening spontaneously. It was being natural. We never started up this. But in a nuclear reaction, we are striking this neutron with a nucleus. Else, this nucleus was not supposed to decay. This neutron triggered this nuclear reaction. So basically, when we are talking about a nuclear fission reaction or the other type of a nuclear reaction, that may be a nuclear fusion reaction, this needs to be clearly understood. This is not a natural process. This we do as our by our choice. What happens and why do we do this? Because this is very important and this is very easily understandable. When we say that this nucleus, let's say, has a mass initially of 10 grams. I'm just assuming this 10 grams, and these two nuclei, along with some particles that are emitted through this decay process, in total are calculated for mass calculations. So these three things: first nucleus, second nucleus, and all these new subatomic particles, they basically were originating from the single nucleus, so they should be having same mass, that is 10 grams. But this is not happening here. It is found experimentally that the mass of these decayed atoms is slightly less than 10 grams. It may be, let's say, 9.5 grams. So where does that zero point 0.5 grams went? So according to law of conservation of mass, mass is neither created nor destroyed, but here it is being missed out. So that zero point 0.5 grams is now converted into energy. So that is where we use a nuclear fission reaction to either generate a nuclear bomb or generate a nuclear reactor, so that we can have utilize this energy in any purpose what we might be interested in. So this equation, it shows a uranium nucleus having a charge of having an atomic number of 92 protons, having a mass number of 235. It absorbs the nucleus, it becomes unstable, and it decomposes and it decays into barium and krypton. These two are known as fission fragments. Fission fragments are nuclei that are obtained after nuclear fission reaction, along with three neutrons. And what we can see clearly is this equation is balanced in terms of atomic numbers as well as in atomic masses. So if I may underline this, 56 plus 36 plus 0 will lead us to 92. That means all of your reactants, the charge of your, basically the atomic number of the reactant is equal to the atomic number of sum of the atomic numbers of the products. Same goes for mass. 141 plus 92 plus 3 neutrons. So 141 plus 92 plus 3 neutrons basically gives us 235. This needs to be clearly understood. So I hope this is clear. Let's move forward. As we have discussed previously, when we are talking about a nuclear fission reaction, there is a slight change in mass. That mass in certain textbooks is referred to as mass defect, and that can be calculated using the famous Einstein's mass energy relationship, E is equals to mc square. Let's say initially your radioactive nuclei was having a mass of 10 grams, and it decayed to some components that have a net mass of, let's say, 9 grams. So that 1 gram, according to this law of conservation of mass into energy, has been converted to energy according to the relation E is equals to mc square, and we can calculate the energy. Mass would be substituted in kilograms, that would be 1 over 1000, and c is the speed of light, that is 3 multiplied by 10 with power 8 meters per second, constant for all nuclear processes. So we can have energy in joules. Let's move forward. If we are discussing the application of a nuclear fission reaction, what a fission reaction, where can it be used? So we are basically explaining a nuclear reactor right here. So this nuclear reactor core is having a controlled fission. We are having a controlled fission reaction here. That means a fission reaction beyond control can be disastrous. Controlled fission reaction here. So we are producing energy in this reactor core using a nuclear fuel. Basically, that is uranium, and that links back to the same equation. Uranium, when it is absorbed by a certain neutron, it decomposes into barium and krypton, along with three neutrons and release of energy. So that energy is basically stored in this reactor core, and then we can have that energy utilized so to power this basic turbine, and that turbine is linked to an alternator or a generator, and then we can have electricity being produced. This is an AC generator. So what's happening is this reactor core is having a nuclear fuel, and as soon as a reactor reaction starts, this becomes heated up. So we are having a coolant here that circulates in this way. That coolant can be sodium vapors, barium rods, and sodium vapors, or mercury, or even simple water that flows through these pipes and then again pumped back into this. So what happens? Water comes or coolant comes here, it absorbs energy, it becomes hot, it passes through this channel here, and then it heats up this water. So this water, as soon as it absorbs heat, there is a heat exchange between this coolant and water. So this heat that is being absorbed by this water changes water into steam, and that steam turns this turbine, and that turbine then is coupled with an AC generator, and we can have electricity. Now, certain components that needs to be explained particularly here. What is a pump? Pump basically circulates the coolant from from into the uh, inside and outside the reactor core. Then we are having a reactor that is basically a fire brick lined and concrete lined reactor that is stronger to withhold the nuclear heat or nuclear energy. Moderator basically is here is graphite. This absorbs extra neutrons emitted from the nuclear reaction. So if certain reaction, for example, fission reaction goes uncontrolled, so moderator controls or regulates the emission of extra high-speed neutrons. Then what is a control rod? Control rod is used to basically control a nuclear reaction. That means whenever we want, we can stop this reaction as soon as these control rods enter this nuclear core. These control rods absorb all the free mobile neutrons, and there is no more nuclear fission than happen in this reaction. Then high pressure vessel is basically uh, there to ensure that no gas or no particle or no energy escapes out from this reaction. So let's move forward. So the other type of nuclear reaction is nuclear fusion reaction. What happens in a nuclear fusion reaction is there are two smaller nuclei, and these two smaller nuclei they fuse to form a larger nuclei, and energy released in this process is far more higher as compared to a nuclear fission reaction. In a fission reaction, we were having a single nucleus that was being broken down into smaller nuclei, but in a fusion reaction, we are having two smaller nuclei to form a bigger nucleus. So theoretically, it is believed nuclear fusion is happening in somewhere in sun, and it is also happening in the creation of a planet. So, what's creation of a planet? What happens on sun is basically there are certain gases, so few name them as hydrogen, and they combine to form helium. We'll see that equation later on. And what happens in the creation of planet is basically leads to the conclusion of theories of star formation, and we are going to discuss them. Theories of star formation, and we are going to discuss them now. This is believed to be happening on Sun, that there are two hydrogen nuclei. Deuterium is an isotope of hydrogen that contains one electron, one proton, and one neutron. These two nuclei are fusing together to form helium with the release of energy, and that energy we can experience quite clearly on Earth. That is basically so much amount of energy that is released during a nuclear fusion process.